In section 3.5, we're going to look at the derivative and further discuss what it means to be a rate of change. So first of all, I would like to make a distinguish between distance and displacement. So let's just say I have some object and it's moving along this curved path and then it stops. Okay? So this path would be the distance that the object has traveled. Okay, so that would be our distance. But when we say displacement, displacement is a straight line distance from your starting to your ending point. Okay, so there is a difference when we talk about distance as opposed to displacement. The first thing that we're going to look at, though, is we're going to look at objects that move in a linear path. Okay? So that's what we call a one-dimensional object, okay, or one-dimensional motion. That would be an object moving in a line. In example 1, we have a rocket that's launched straight up into the air. Its position S in meters at time t, where t is in seconds, is given by this graph below. Okay? S of 0 represents the initial height of the rocket, and the t-axis represents ground level. So here, the t-axis and the s-axis. Okay, so what do these given points represent? Well, this first point here is about 0.7. Okay. So this is about 0.7, comma 10. And the other point is 1.6, comma 15. So what the first point represents would be at 0.7 seconds. Our rocket is 10 meters from the ground. Okay. So when we look at the path of this rocket, it's not that parabola shape. That's not its path. That's just giving you, for any t value, its height or its distance from the ground. So the actual path of the rocket is going straight up and then it comes straight down. Okay? And then it hits the ground. So this is the actual path of the rocket. This graph just represents the distance from the ground for any time t. And then the other point would be the same. It would be at 1.6 seconds. The rocket is, in this case, would be 15 meters from the ground. Okay, so what we're going to do is we're going to let S equal some function of time. Okay. And let's look at this graph. Remember, if I draw a line through the 2 points, that line would represent a secant line. So this secant line, its slope would be, I'm going to write m secant for slope. Remember, that's going to be the change in the y values, which are s in our case, over the change in t values. and that's going to be our average velocity. From here, why don't we look at this point as being our point A to this point here, which I will call B. Now the distance from A to B, I'm going to call that distance, this distance here, delta t. So if that distance from A to B is delta t, then another way to write B is that's equal to A plus the distance delta t. And that delta t is just the elapsed time, because remember t was time. All right, so now let's look at the first point. And here, I think I'm going to use blue. So at this first point, if I draw my tangent line, so for this tangent line, its slope is going to be our instantaneous rate of change. So the slope would be the derivative at that point A. Now this is seems kind of silly, right? I'm just going through a lot of notation, but there's a method to my madness, because we're going to be using this notation when we define like a position function, velocity, acceleration, and so on. So now with this point A, it's going to correspond to a y value on the graph, which is our f of A. And since B is the point A plus delta t, when I look at the y value that corresponds, it's going to be f of A plus delta t. So this distance between the y values, this is the distance of s. It's delta s. It's how our s values are changing. And that delta s is our displacement. All right, so this is just a bunch of notation. And this is where we use that notation. A position function, okay, would be the position of an object moving along a straight line. Now here we're talking about straight line motion at any time t. And we'll call that equation S of f of t. Displacement is going to be the displacement of the object between A and A plus delta t. Okay, so remember delta t is the elapsed time. And delta s would be our displacement. The average velocity is given by the change in displacement over the change in time. And then the instantaneous velocity is given by that limit. So the instantaneous velocity, we're going to use v for velocity. Remember, that's just the derivative of our function s. So let's kind of put all of this together in example 2. In example 2, we have the position of a moving object, and we have the function. The position is negative t squared plus 6t. S is in meters. We're only concerned with t values from 0 to 6 seconds. In part A, we're supposed to find the average velocity over the time interval 3, 4. So this should look really familiar to you. This is what we did in 2.1. So the average velocity would be s of 4 minus s of 3 over 4 minus 3. And it turns out that that's negative 1. But since we're talking about velocity, we want to add the units meters per second. In part B, we're going to find the average velocity over the time interval from 3 to 3.5. So that's s of 3.5 minus s of 3 over 3.5 minus 3. It turns out to be negative 0.5. Again, this is meters per second. C, we're going to find the average velocity from 3 to 3.1. So s of 3.1 minus s of 3 over 3.1 minus 3. That's going to be equal to negative 0.1 meters per second. Okay, so finding the instantaneous velocity, that's just the derivative. So the instantaneous velocity is going to be the derivative of our function s. So it's the derivative of s, and that's just equal to negative 2t plus 6. So we want to find the instantaneous velocity when t is equal to 3. So that would be v of 3, which is negative 2 times 3 plus 6. That's going to be equal to 0. And then meters per second, right? Because we always want to have our units on there. Which makes sense. If we look at parts A through C, as we get closer and closer and closer to 3, we're getting closer and closer to 0. Let's look at this following definition that kind of describes what we were doing. This is the definition of velocity, speed, and acceleration. So to find the velocity, if you do have a position function, okay, to find the velocity, you would take the derivative of your position function. To find the speed, and this is going back to vectors, speed is the magnitude of the vector, which is the absolute value or its length, and speed would be the absolute value of velocity. Acceleration would just be the derivative of the velocity or the second derivative of the position function. So if you have a position function, to get velocity, you take the derivative. To get acceleration, you take the derivative again, or the second derivative. In example 3, we're going to look at an object that's moving horizontally. So it is linear path. T is in seconds. We have this position function, s of t equal to t squared minus 6t. And we're only going to consider the function from 0 seconds to 6 seconds. Now we're going to assume that if the position function is positive, then the position of the object is going to be to the right. Okay, because remember, this object is moving horizontally. So if the position function is positive, the object is to the right of the initial position. If the position function is negative, the object is to the left. Part A asks us to graph the position function on that time interval. So this position function is a parabola opening up. Here, let me just do a quick sketch. But remember, we're only graphing this function from 0 to 6. And at 0, we're at 0. When t is 6, we're at 0. So remember, this is t, this is s. And it opens up. So the parabola does something like that. Since we're only graphing from 0 to 6, that's all we need. This parabola does keep on going, right? It keeps going up, but that's actually not part of our graph. Our graph is just from 0 to 6. So what you should notice is that the position function is negative. That means from 0 seconds to 6 seconds, the object is to the left of the initial position. In part B, we're supposed to graph the velocity function. So I need to take the derivative of my position function. And if we go back up and look at the position function, which is t squared minus 6, so the velocity is going to be 2t minus 6. And that would be a linear function. Again, we're only graphing it from from 0 to 6, right? So when t is 0, we're at negative 6. Oops. And when t is 3, we're at 0. When t is 6, we're at positive 6. Okay, so this is going to go something like that. Again, we're only graphing from t0 to t6. So although this line technically keeps going in both directions, we don't need that part of the graph. So this would be at 3. Well, when we look at B, it says to determine when the object is stationary, moving to the left and moving to the right. So we get the movement from the velocity. When the velocity function is 0, that's when the object is stationary. So notice that the velocity function is 0 at 3 seconds. So the object is stationary at 3 seconds. Now where the velocity is negative, which would be from 0 to 3 seconds, that's when the object is moving to the left. So it's going to be left from 0 to 3 seconds. Where the velocity is positive, that's where our object is moving to the right. So it's moving to the right from 3 to 6 seconds. That's not the same as the position function. When the position function is negative, it just means the object is to the left of the initial position. It doesn't say anything about the direction that it's moving in. So we'll put that all together in just a little bit, but let's go ahead and look at C. We're going to graph acceleration. So in C, the acceleration is the derivative of the velocity. And in this case, our acceleration is just 2. It's constant, it's not changing. But remember, we're going to graph this from 0 to 6 seconds. So if this were 2, this is what my acceleration would look like. And again, it's a horizontal line that just keeps going in both directions, but we're only concerned with the graph from 0 to 6 seconds. Sorry. Okay, so we need to describe, in part D, we're going to describe the motion of the object. So it's just in general. What does all this mean? Well, since the position function is negative, let me just go ahead and draw a little sketch of this. Let's say that we start here at t equals to 0. Because the position function is negative, that means that the object is always to the left of the initial position. Now from the velocity, I see that from 0 to 3 seconds, the movement is to the left. Okay? And then at t equal to 3 seconds, the object is going to turn around and come back. Notice that it's still to the left of the initial position. But now from 3 seconds to 6 seconds, the movement is to the right. Okay? And then once we're at 6 seconds, the object is back at the original starting position. Okay? So the object moves to the left. At 3 seconds, it turns around and moves to the right. At 6 seconds, it's back at the starting position. So what we're going to do next is we're going to look at another application of instantaneous rate of change, or the derivative. And this one is not really the motion of the object. What we're going to look at here is we're going to look at an application in economics or business, and it's going to be the average and marginal cost. So let's say you have some cost function C. And what it's going to give you is the cost to produce the first X items. Well, oftentimes you want to know what is the average cost to produce just one of these X items. So the average cost is noted as a C with a bar, so C bar. And all you do is you take your cost function and you divide by X, where X is the first X items. Now, if you take the derivative of your cost function, that's your marginal cost. The marginal cost is going to be the approximate cost to produce one additional item. In business, what you want is you want your marginal cost to be lower than your average cost, because that means that the more items you produce, the less it costs to produce each item. If you find that your marginal cost is actually larger than your average cost, then you better rethink your business. In example 4, we have this cost in dollars and we have a cost function. So part A, we want to determine, In part A, we want to determine the average and marginal cost functions. So the average cost is just going to be the derivative over X. So I'm writing just the general formula for the average cost, which would be 0.01 x squared plus 25 x plus 50, and we're going to divide all that by X. So let me simplify this to be negative 0.01 x plus 25 plus 50 over X. So that would be my average cost, and then the marginal cost is the derivative of the cost function, which would be negative 0.02 x, oops, should have left some more space, plus 25. So we have our average cost and our marginal cost. In B, what we're supposed to find is the average and marginal cost when X is 100. So it's going to be the average cost to produce one item if we're producing 100 items, and the marginal cost would be the 101th item, the cost for the 101th item. So the average cost, if X is 100, and here we'll just plug that into our calculator to get 24.5. And the marginal cost, which is just the derivative evaluated at 100, comes out to be 23 in your calculator. So what does that mean? It means that the average cost to produce one item is $24.50. Okay. The cost to produce the 100th and 1th item should be about $23, which is good. That marginal cost is lower than the average cost. In part C, we're going to do the same thing. We're going to figure out the average cost, but this time we're going to look at the average cost when we produce 400 items. So in our calculator, that's about $21.13. And then the marginal cost is going to be 17, which is even better. And this is how it's supposed to happen when you produce something. First, you have to set up your factory, set up all your machines, and you have this initial cost that's usually pretty high. So the more items you produce, actually your cost should go down per item. And in this particular model it does, which means if this were a real business, I would be making money. So it's the same thing. Average cost would be $21.13. The marginal cost, which would be the cost to produce the 401th item, would be $17. Okay, so that's it for this section.